Guys, welcome back to another video here from the Off-Grid Garage in beautiful sunny Australia. It is freezing cold outside. It was like 7 or 8 degrees last night. Hey, that is cold. What are you saying? And we have now fully charged our Frankenstein battery. I haven't. And this is no one's fault but mine. Remember I told you I have pre-charged. I was a bit scared to take off this metal lid from these blank terminals. Remember, I've told you I've pre-charged all the batteries here to 3.45 volts with more or less absorption. Well, it turns out, let me show you this on the knee. It is now like 1.5 days later since we installed the battery, and I hooked up the power supply to keep the battery on a charge and let the knee do the top balancing. Well, we are still at 141 millivolt deviation here, so it hasn't done much actually. It came down from 250 or something, but last night it was still on 160 millivolt, so in 12 hours 20 millivolt. And we can see cell number 9, 10, 11. They are under 3.4 volts, far under 3.4 volts. And if you remember our list, cell number 8, 9, 10, 11, these are the EVE 304 ampere hour, the oldies, which were bought in 2021. Well, it turns out they were not that charged as I thought, obviously. So what I did last night, I actually installed our CKE tester here and just connected it to cell number 8 and let it run. And it kept running until I went to bed at 11:30 or so. And this morning it showed 41.6 or 41.5 ampere hour. There was like 50 ampere hours missing in these 4 batteries. And the poor old knee active balancer had no chance to balance this. No balancer in this world can balance this in a short amount of time. And as you can see, the balancer is still running. It is still trying to balance now 9, 10, 11. The last 3 remainings, but obviously with the 4 amp it will take another couple of days or so. And I really want to do the full top balancing today because I want to start the capacity test on this beautiful battery. And you can see the knee is still flashing green. It is trying hard. But to equalize 40 ampere hours for 3 cells, this will take forever. So we have to, well, even with this small CKE tester, the 40 ampere hours, it charges with 5 amps, 40 ampere hours. This is 8 hours per cell, right? 8 hours per cell. Okay, I probably use the variable power supply and connect it to one of the other batteries and let the CKE tester run and have the big Chinese cracker connected to the 3rd cell and charge them all at the same time, and hopefully we can start within an hour or so, or maybe 2 hours or 3 hours or so. It is early in the morning anyway now. So we've got enough time today to do that. So let me separately, individually charge these cells now to a 3.51. Pretty much in line with all the other cells, around 3.5. And then we keep bringing them slowly up. So the knee has actually a chance to balance something here. And as much as I like the knee active balancer, I think in these cases it is not as efficient, because the main disadvantage of this balancer is it balances only 1 cell at a time, 1 cell. And here in this situation we have many cells on a high voltage and it can balance only 1 at a time. And at the beginning the BMS turned off quite often because one of the cells hit the 3.65 volts and the knee was not able to prevent this, because there were too many cells to look after. So if you have only 1 cell peaking, it can work on this 1 cell with 4 amps and it will work perfectly. But if you have a second one, well, then which one should it balance first, right? Discharge first. It can only alternate between these 2. If you have 3, 4, 5, 6 cells on a high voltage, it cannot handle this anymore. And I think the capacitive balancers, the 5 amp balancers, are working better here because they balance all of the high voltage cells at the same time with a lower current, but they do them all at the same time. Anyway, let me bring these 3 cells up to voltage, and then I'll talk to you again. It is now 10 o'clock in the morning. It may take 1 or 2 hours. Power supply, big Chinese cracker, the small CKE tester, all charging the battery now. Yeah, plus the actual power supply, the whole battery. Look at this setup. 2 millivolt deviation we have at 3.8 volts around. That's not too bad. It is already 1:30. So it took a lot longer than expected. Anyway, we're going to increase the voltage here slightly to 56 point something, because we want to fully top balance this battery. So 3.6 volts would be ideal, and then make sure all the batteries are top balanced, and then we go from there. So we are at 3.57 with 1 millivolt deviation. The knee. Who said something negative about the knee? Not working. Okay, let's go a little bit higher. Okay, my friends, after top balancing the Frankenstein battery for the whole day, basically, it is 5 p.m. now. We have finally made it. So the BMS shows a 13 millivolt deviation at 3.64 volts. I was just going a little bit too high, and we have now a pack over voltage protection, so the BMS has actually turned off charging. But you can see here the knee balancer, 2 millivolt deviation it gives us, so we are close to 3.65 volts with all the cells now. It took me really the whole day long to recharge these 4 cells and then balance everything out. But, you know, on the other hand, if you put all the batteries in parallel to begin with, this takes a long time as well. And I never did it. I always put the batteries in series and then charge them up and see what happens. Sometimes they're lining up perfectly fine. Sometimes I've got these issues like today. And I need to bring some of the cells to the same voltage level as the other ones are. And then we can start charging them up all together. But we have now really fully 100% charged this Frankenstein battery, and we are going to discharge it right now. Before we do that, I want to do something else. Hang on. Exactly. Internal resistance. So, and we want to measure the internal resistance of all the cells now before we start discharging, because we are 100% state of charge, and then we do the same when they are all empty. Okay, let's calibrate this to 0 ohms. Okay, and I have I have disconnected all the balance cables. I have disconnected all the balance cables from the BMS, so there's no connection from any of the balance cables to anything. The knee is disconnected, cables are lying there, so all the cells are standalone. There's no circuit, anything, any electronics connected anymore. They are really just bare raw cells now. Okay, we want to start with cell number 1, which is our negative. And I'm trying to measure from the terminals directly, not through any bus bars or screws or something. So, cell number 1, which is the wrapped 0.23 milliohms. Okay, I'm writing this all down now, and I'll see you in a second. Okay, I have measured all the internal resistance of all 16 cells and also measured the temperatures. We are around 19 degrees Celsius here at the moment, battery temperature. And these are the results of the internal resistance. This is how far we spread apart in internal resistance. So I think this is pretty good actually. For this bunch of random batteries we put together here, having these internal resistance which are so close together, I am impressed. Let's do another quick test here. I want to measure the internal resistance of the whole battery. So we would have an internal resistance of the whole battery, including all the bus bars, screws, connectors, terminals, everything, of 5 milliohms. 5 milliohms internal resistance. Wow. That would mean at 100 amps we would have a loss of 50 watts of the whole battery. 50 watts. At 200 amps we would have a loss of 200 watts with the whole battery. That sounds a lot to me. So, and now we have the situation, the battery is fully charged, all the cells are on 100% state of charge, and there is some wrong information out there. I have read all the comments under the video, what will happen when we discharge, when we charge it, when we discharge it. And most people got this right and said, well, it all depends on the weakest cell in your battery pack. This will then determine, or this will dictate, the whole capacity of the battery. So if you have one cell in there with only 250 ampere hours, you cannot discharge any further than 250 ampere hours then. And this is nothing different to any other battery bank you build, any other battery you put together. It is always the weakest cell in your pack which determines then the whole battery capacity. And because we have a mix of 280 and 304 ampere hour batteries here, obviously we cannot discharge the battery any further than 280 ampere hours. And the 304 ampere hours, they will have a bit of a rest capacity then left at this point of time. So, and here's quickly what we have. 3 the same batteries, and one of the batteries is a bit higher. Yeah, so this one has more capacity. And at the moment, we all have them 100% charged, so they have all 100% state of charge. 100%. If I discharge the battery now to 50%, these 3 batteries may have 50%, but this one may have still 55 or 60%, because it has a higher capacity to start with. And the same at 0%. When we have fully discharged the battery, these batteries are empty. They cannot deliver any more power. But this one may still have 20% state of charge left. But as we just said, the batteries with the lowest capacity determine the capacity of the whole battery bank. Because we have a series connection. Here's my negative, here's my positive of the whole battery. So all our batteries with 304 ampere hours, they will still have a bit of capacity left when we fully discharge the battery. And one of the 280 ampere hour batteries will trigger the BMS, because this cell has then reached 2.5 volts and the BMS turns off. And we cannot technically use any of the rest capacity of the 304 ampere hour cells. And quite a lot of people have actually said we will need a lot of balancing power here for this battery. Maybe even several balancers in parallel to get this beast under control. But as you have just seen with the top balancing we have done here, this was not different to any other battery we have built here in the off-grid garage. You don't need any stronger, any more balancing than with a normal battery as well. Well, you could now argue, if we reach the 0% state of charge with these 3 batteries and this one has still 20% left, why not get this energy out and get it into these batteries with a balancer? Yes, we could let the balancer run all the time, and it would technically take away some energy from these 304 ampere hour batteries and put this in the 280 ampere hour battery, and we could get the battery to run a little bit longer than without this balancing. But this all depends on the load you have connected. If the load is very small, smaller than your balance current, then it will work. Then you could actually fully discharge this battery as well and take the rest 20% out of this cell and spread it across these cells, so none of these cells actually hit the 2.5 volt and the BMS turns off. And only if these 20% are used as well, then one of the cells will hit the 2.5 and the BMS will then turn off. But if you then recharge your battery, these 3 cells will actually reach the 3.65 volts the first, while this one is only at 80% of the capacity. So you end up with the same dilemma again when you fully charge the battery when you do that, because you have actually destroyed your top balancing. The batteries are then bottom balanced. You had them all on 0% state of charge. And then charging them up, you need to top balance them again. And we have 10 280 ampere hour cells and 6 304 ampere hour cells. And then you are right, that would mean a lot of balancing if you want to do that. But then you need also to consider that such a large battery, this is like 14 kilowatt hours of energy now. Usually you don't build such a large battery when you have only a very small load connected. This is a battery which can supply power to your house. So you're talking about 100, 150 amps maybe charging or discharging power. And we just said the scenario where we take away energy from the higher capacity cells and spread it across the other cells makes only sense if your load is lower than your balance current. And now again, 100 amps discharge current. This is 5 kilowatt for such a battery. You've got 2 hot plates running and your microwave. That's 5 kilowatt. So you would need to find a balancer which can actually balance larger than 100 amps. Otherwise, one of these cells will hit 2.5 volts. So while there is 100 amp going through this series connection, you need to have a balancer taking away this energy here and put this into these cells at the same time in a faster pace than we discharge these cells. And quite frankly, this is impossible. We will not find a balancer or even a stack of balancers which can deliver 100 amp of balancing current. And furthermore, you're not only discharging this one with 100 amps through your normal load, you would also need to take away 3 times 100 amps and put this balance current into each of these cells to prevent them from shutting down the BMS. So 100 amp load plus 3 times 100 amps for the balancer. This would make 400 amps for this one cell. Quite frankly, not possible and unhealthy for the battery. We would exceed the 1C discharge current maximum for these battery cells by a lot. And you can see this whole scenario doesn't make sense. Once you have top balanced your battery, you only discharge until the first of your 16 cells hits the 2.5 volts, and then you call it. All the other energy is still in the other 15 cells, cannot be used. And again, this is exactly the same as in the battery shelf, as in the Jackie battery, in the Mason batteries, in the Seplos, in the QSO. Once the first cell hits the 2.5 volts, the BMS turns off, and that's it. And no balancer on this earth here can prevent this from happening. Okay, this only as an explanation around the series connection of battery cells and balancing them at the top and at the bottom. This, as we have just seen, this does not make sense. So we stick to the top balancing. Everything, all the technology, the BMSs, the balancers, they all do only top balancing. Bottom balancing is something from the past. This was before we had BMSs, electronics, balancers. Everyone was using bottom balancing. But these days, top balancing is the way to go. Okay, without further ado, let's get started. I have also connected the Victron Smart Shunt, our test shunt, in between, and please remind me that I have to reset the history, otherwise you're giving me a hard time again. And as always, I connect this battery now to our Powerwall 2.0 or whatever it is, and we use the Xijia Inverter here to fully discharge the battery, pumping all this energy into the Tesla. I actually didn't charge last night, so the battery sits on 35-ish% or so. So there's enough space to take all this power, all these 14, 15 kilowatt hours, whatever it delivers here. And we want to discharge the battery with 0.2C, which is around 56. Yeah, thank you. So I'm trying to match the charging current of the Tesla, so we can actually discharge the battery here with around 55, 56 amps. And then we are going to see how long it will take. Probably 5 hours, so it will be a late night show. It's already dark. I started this morning with this whole project. I shouldn't have done it. But I don't want to leave the battery sitting here on 3.6 volts for too long, so I'll start the test now, and it will take whatever it takes until we are done. I've done it. All the history is reset. Everything is 0. We're on 100% state of charge. I've got the extension cable to the Tesla. Got this all plugged in to the Xijia Inverter. Xijia Inverter is the best. Torqued everything with 4 Newton meters. And we probably have to turn on the BMS. So we should already see some current flowing now into the inverter, 15 watts. All right, we have started charging. Okay, it's ramping up. 40, 45, 11 amps. It's only a 10 amp circuit breaker in this adapter I'm using. Cell voltages, 108, 110 millivolt deviation already. That's not good. What is our highest cell? Is it jumping back and forward? That's good. 5, 12. Okay, I would say we leave this running here for maybe half an hour, and then we will have a look with the infrared camera and see if we can see any hotspots. We probably should do it right now. Okay, so before we leave this all sitting here for 5 hours, we want to have a quick look with the infrared camera first and see if there's anything heating up. So far it doesn't look too bad, but let's go a bit closer. So here's our BMS. This little transformer heats up quite a lot there. And we've got the negative cable warming up. I mean warming up, and we are talking about 24 degrees, right? 24 degrees. Well, let's see what's going on here in the battery. So far everything seems good. Hotspot 22 degrees. Okay, that's fine. Here's some cables. No, that all looks good. Yeah, Medi's cables warming up now, 21 degrees. That's all fine. Just want to make sure I haven't got a hotspot here with the smart shunt cable connection there. Positive negative cable going up. That's the 230 cable. 28 degrees is our hotspot here. Everything else all good. Alright, see you in half an hour or in an hour or later. So we have now charged for a bit over an hour. We are down to 73%. And I'm just doing another check here with the infrared camera. But the battery looks fantastic. Very uniform. No big hotspot. There's the one cable there, 27 degrees we are talking about. I'm not considering this as a hotspot. BMS doesn't get hot, nothing. Smart shunt, cables, all good. The last 10% of the Frankenstein battery. And I'm back. It is almost, it is 11 p.m. And we probably go another 20 minutes or so until we shut down. So we are just under 3.1 volts with cell number 1. I watched the BMS situation here from inside the office, and I must say cell number 1 and 2 are actually our weakest cells in the whole Frankenstein battery. Cell number 1 and 2 are the REPT 280 certified cells. So they have the lowest voltage and they will trigger the BMS to shut down. I'm pretty sure. It is not the lithium, the bloated, swollen, double pregnant lithium cells. They are nice in line with all the other cells. We have pulled 250 ampere hours so far. Let's have a look at the smart shunt. 246 ampere hours pulled, 12.8 kilowatt hours, and still going. We are at 50 volts, just over 50 volts. Okay, let's use the FLIR camera and do another flyover. See how the temperatures are after 4 hours. How long are we? 4 hours and 46 minutes so far. Wow. It looks like the cells have heated up a little bit on the left, where the BMS is connected to. So in the top left hand corner, this is cell number 1 and 2, which is the lowest voltage cells at the moment. And they are the warmest with, it's definitely under 30 degrees because this is our hotspot there. This is the terminal, the main negative. Yeah, there's nothing. The BMS itself, nah, all good, all cool, under 30 degrees. I think this is the best battery we have ever built. Isn't that amazing? Alright, it really doesn't look too bad. So I'm actually really surprised that all these random cells are holding up that nice. We've got 117 millivolt deviation now, so cell number 11 is the highest, cell number 2 is the lowest. Got 25 ampere hours to go. This might be another 15-20 minutes or so maximum. And look, so far you would not be able to tell which battery is a 304 ampere hour and which is a 280 ampere hour battery. They are all the same. I did some changes in the settings as well during the discharge. I set the trigger force charge here to 0. I think this is when the BMS usually turns off. Charging or the discharging disconnect at 0%, so we really fully discharge. And I have also set the cell under voltage protection from 2.7 to 2.5. We don't want to forget that. Yeah, apart from that, man, it's working great. Best battery ever. Who would have thought? Okay, we are just under 50 volts now, but not under 3 volts per cell. They are still holding up. It's incredible. 17 ampere hours to go. But I doubt we will get the 280 ampere hours. We are 261.5 now. There will be another 18.5 ampere hours. And we are under 3 volts now with these two cells here. So we won't get the 280. I was hoping for 280 plus, because all the cells individually, they're all measured above the 280 ampere hour. So in theory, we should get this. And as you have seen, there's no issue with any bus bars or cabling or something with these two cells. They are perfectly fine. They are in line with all the other temperatures around them. So we are at 270.5 ampere hours discharged. I just had a suspicion that the BMS may shut down if we reach 0%, because, well, this is one of the protection parameters now. Yeah, I set this to 0%. Cell number 1 is at 2.83. It's still holding up okay. We're still pulling 58, 57 amps. And we are over 271 ampere hours now. But the most amazing thing of all this testing here is the Xijia inverter, right? I mean, it's a 3 kilowatt inverter and it's running on 2.7 for the last 5 hours and 12 minutes. Full blast, full power. And it does it every time we test the battery here, every single time. It is such an amazing inverter. Never had an issue with it, apart from the little pody inside, which regulates the output voltage. But this was quickly replaced. What an amazing product. I linked this down below just for you guys. If you want a really good inverter, the Xijia inverter, they are amazing. It's like the Peter. They are good. Okay, back to serious. Under 2.8 volts, 14 kilowatt hours, 272.6 ampere hours we have pulled. I can hear the fans are spinning down of the inverter now. It's getting hard to maintain the 2.7 kilowatt the Tesla demands. We're almost at 60 amps now. Voltage goes down, amps are going up, power stays the same. So now we are really in the steep area of the curve for this cell number 1 and cell number 2 actually. But we've got cell number 15 and 16, the other certified cells under 3 volts. And the oldies, okay, they are 304 ampere hours. Okay, we cannot count them. Yeah. See, cell number 3 and 4 are 304s, and cell number 8, 9, 10, 11, they are 304s. And of course, they're staying above 3.1 volts now. So now we see the spread. We've got 400 millivolt deviation almost. And this is expected, because we still have like 24 ampere hours left in the larger capacity cells. Oh no, we are at 0% state of charge. 1.1 ampere hours to go. Then the BMS has counted 280 ampere hours, fully discharged the battery, while the smart shunt has counted 274.7. So there is 5 ampere hours difference. That's fine. So cell number 1 is now in a free fall, 2.65 volts. Yeah, we can reach the 276 ampere hours. Everything is on zero here, 0 ampere hours left, 0% state of charge. Usually you wouldn't discharge the battery that much, but this is the maximum capacity the battery can deliver. And let's see when the protection kicks in. Now, something has shut down. It's not the BMS. I think it was the inverter. Well, the inverter is off. Everything is off. Okay, guys, I don't know what happened actually, but we still got 2.6 volts in cell number 1, so it was not an under voltage protection. Something else happened. The smart shunt is definitely off, and I think the BMS has turned off as well. I don't know the reason for it, because we didn't reach any protection. The charge MOS is still on, discharge MOS is still on. But I'm not sure if this is still a live picture. I doubt it is. It looks like it's frozen. I don't really know what has triggered this shutdown of the BMS here. That is a bit of a mystery. So we had 14.2 kilowatt hours and 276 ampere hours pulled from this battery here, from the Frankenstein battery. So that's not too bad. I'm a little bit disappointed about cell number 1 and 2 actually, that they shut down or they were so low. Certified cells, brand new ones, 2 or 3 cycles done. I don't know why. I'm also a bit disappointed about the BMS shutting down for no particular reason. Well, excuse me, this is now Andy from the future. I've got something for you. So it is now the next day, and last night I couldn't really find out why the BMS did shut down, and I had a discussion with Gobel Power as well, with Daniel again, and he pointed out that there is another setting which could be responsible for the shutdown of the BMS, and I think he's absolutely spot on with that. So in the software settings tab, under the CVL, the CCL and the DCL for the Victron system, there is also the discharge cutoff voltage, which sits on 44.8 volt. And I think this was the reason the BMS shut down. Even it looked like we didn't reach the 44.8 volt last night. But I keep this in mind, and in one of the next tests I want to do with this battery, we discharge it again to 40 volts or 2.5 volts, whatever occurs first. And we will set this one here, of course, then to 40 volts. Yes, we want to do some more testing with this battery, of course. I want to do a high amp discharge test. Let's see if we can put some stress on Maddie's bus bars. Oh, it is 11:45. The last thing I want to do before I go to bed is measuring the internal resistance again of all the cells while we are completely empty, just to compare this to the other values we had when the battery was full, if there's a difference or not. All right, I've got the results here on a paper. I put them here on the screen for you. So this is the one at 100%, and these are the results at 0%. So we cannot really tell. That looks random to me. They almost haven't changed. Cell number 8 is a bit high. I measured on different locations. Cell number 8 is an EVE oldie. But I couldn't get it further down than 0.29 milliohms. So yeah, this, I don't know, this doesn't lead to any conclusions, I would say. So, and here again, we are exactly at this position now, 0% state of charge of the whole battery, but these 304 ampere hour batteries, they still have a bit of capacity left, like 24 ampere hours maximum. And now we are going to fully charge the battery again, so we are adding another 280 ampere hours to all the cells, and they all should meet again at 100% state of charge, more or less. Yeah, the top balancing is still intact, and we will check this in the next couple of days then. And guys, until then, as always, thank you for watching. Thanks for all your great support here on the channel. It is 1 minute before midnight. Woohoo! We will of course continue our Frankenstein Battery series here, doing more testing. Anyway guys, until the next video, you stay charged, stay safe, and thanks again for watching. See you then. Bye bye. someone has found out about my address and sent me this. So whoever did this, thank you very much for that. Thanks a lot.